The purpose of this lab is to apply the principles of conservation, or the loop rule, and current conservation to study the dynamics of circuits, including potential difference, resistance, and currents. We will experiment with these relationships as we create new series and parallel circuits. We'll also be examining the effects of resistors and capacitors. The loop rule states that the potential difference round trip across a battery is zero. The node rule says that the current entering a node is equal to the current exiting the node. Capacitance is the measure of how much charge can be stored on a capacitor per unit of potential difference, and resistance is the measure of opposition to the flow of the current. In part 1, we made a simple series circuits with two 1.5 volt batteries. The first resistor is 47 ohms, and the second resistor is 100 ohms, and then we also had 2 ammeters. We predicted the current to be 0.0204 amps, and the actual current ended up being 0.0145 amps. And when we did this in reverse, it was negative 0.0145 amps. In part 2, we now open the circuit and we replace the second ammeter with the voltmeter. And our potential difference was still 3 volts and our current was 0 amps. In part 3, we found the potential differences between the different points, and on the top it is graphed and the equations are on the side. And underneath, the loop rule says that the sum of the potential differences should be equal to 0, and when we sum all the potential differences up, we see that it does equal 0. In part 4, we added the second ammeter back to create a node, and this actually creates a new parallel flow of the circuit, so that is going to increase the circuit. It is also important to note that the resistance of the ammeter is very small. In part 5, we found the resistance of each component, and to do this, I use Ohm's law to convert the equations to find the resistance for each piece. In part 6, we made 2 RC circuits, and they had the same battery and the same capacitor. The only difference was the resistance of the ohms of the light bulb. And we can see that the greater the resistance is, the longer it's going to take for the capacitor to charge. Our lab question asks, what if you changed a capacitor with no resistor in the current? How quickly would our ideal model predict the capacitor to reach full charge? Will this prediction happen in real life? And we said that in real life, an ammeter resistance is not 0, so the resistance will be greater than the experiment. This also means that the current will be smaller, and it is also important to note that the wires will have resistance, so this will also contribute to the total resistance of the circuit, and it will also decrease the current.